So yeah, last time I said that your retarded propagator in a general theory would look like something of this kind. Maybe I should write it in a in a better way. And today, let me. So we said that GR omega K in any interacting theory should take the following structure. There should be a quasi-particle pole weight. It's called the residue of the pole, which is positive, and also it satisfies this identity that 0. I said I'll give a proof of this: 0 less than equal to Z less than equal to 1. And then there are some, maybe I could put it as some kind of discrete poles. There's this kind of quasi-particle poles, and there is a sum n and omega minus omega naught K minus imaginary, so minus sigma omega sigma K. Sigma omega K is a more rather, but because I'm a pole, I would rather say it is sigma K. We said that something of which is, and this actually is has a real and imaginary part. So as a result, you find these kind of poles. The poles are at omega naught K plus some RK minus plus minus. So I would put this as plus minus, sorry, and then this as minus IK. So these are the poles. These are the poles of the retarded propagator, and with residues which are Z of K. So this is what we said, that it corresponds to quasi-particles, because now your particles in a non-interacting theory, we saw that GR takes a very nice form. In a non-interacting theory, GR omega was simply minus omega minus proportional to this omega minus omega naught K plus I epsilon and omega plus omega naught K plus I epsilon. So we had these poles, right? This was the structure of GR omega, and this is something that becomes like this. And of course, there is this corresponding other pole that, and sigma K is the real part of sigma K is this, and imaginary part is something this. So this is how the pole structure will look. And but in interacting theory, so in the non-interacting theory, it was just below the real axis. But in a non-interacting theory, it gets a finite width. And this corresponds to when I do when I go to real time. So instead of sine omega naught T, they will look like sine. I would call these as omega K. Or real omega K, if you put it, or let me put it as omega star K. So this is the modified thing, omega star KT. And then this would give me some damping amplitude, which is IK times T. And because this is positive, I get so this is going to decay in time, right? This is what we argued, that this would be this is simply the Fourier transform of this object in real time. If I transform omega to T, I get this. So I find an oscillation. The frequency of the oscillation is the modified energy of the quasi-particle. Instead of following a dispersion relation with omega naught K, it follows a different dispersion relation, which is sort of denormalized dispersion relation by the interactions. And it also decays. And the decay interpretation of the decay was that it can mix with multi-particle states. So one particle, a single electron, can decay into two electrons and a hole, right? So these are the kind of it will be superposition of multi-particle states. And this is sort of the reason it decays in amplitude, because as time progresses, mixes with them. And this is the kind of behavior that you get when you look into retarded. So if you should try to measure something, so by any measurements, you should be able to understand what is the quasi-particle structure of the medium, right? By looking at a retarded response or response to it. This is something that is going to be useful for us, because one of the ways to understand what are the elementary excitations of a system, what is system made of, then you have to simply compute something like a response. So you can, so one easy way to do it is to simply, like take a material and subject it to some time varying electric magnetic fields, for example, and measure the charge density, how it charge and currents that are being produced. So if you do that, then that's a very realistic measurement that you can do. And based on that measurement, you should be able to similarly understand what are the things made of, what is it. So what are the elementary excitations? Something that we should come back to it. We will. So there is, if you find many condensed matter textbooks, I found many condensed matter textbooks write this very nice comment that there is something called a density response that's one of the fundamental things. And they say that if you understand this and its analytic structure, you basically understand all of condensed matter physics. So that's actually not an overstatement. It's a lot of physics is contained in this, actually, in this time dependence that you see. But okay, so now what I also said that this is not the full story. You should expect also some branch cuts. And the branch cuts are, I said, would be something like this. So let me explain where the branch cuts come from, okay? So one way to think about this, so suppose you have GR omega K, the one way to understand this, you are imparting energy H bar omega and momentum K, H bar K into the system, right? Now, suppose you keep K fixed, right? If I keep K fixed and look it as a function of omega, keep K fixed and see in omega and study omega dependence. So what you expect is that whenever omega is the same as when omega is equal to real part of omega star K, when omega is equal to that, you will see an enhancement of the response, because then the particle is nearly on shell and it's carried by a real particle. And so this energy is being transmitted by a real particle. So the response is being carried out by the actual propagation of a particle. So this is where the pole is, right? And if you plot the imaginary part of GR omega, then it will, so it simply comes from the fact that if you take omega minus real omega star K minus I imaginary omega star K, right? How it will look like if I take the imaginary part of this, it will look like imaginary omega star K times omega minus real omega star K whole square plus imaginary omega star K. And if you plot it as a function of omega, it should look like a bump like this, right? This is imaginary GR omega plotted as a function of omega. It will have a bump somewhere here. So let me put it as a mod for the moment. So you will see there's a bump, and this bump has to do with this quasi-particle pole, right? And the width of the pole is essentially this imaginary part. So this gives the epsilon width of the. So essentially, this is the structure that you will see if I look it as a, if I look go to Fourier space. This is a bump and with a width, and this width is the decay amplitude. The decay is related to, so imaginary omega star is essentially nothing but 1 over tau, the decay time of the particle. So this, so the smaller the width is, the long-lived the particle is, and the broader the width is, the more short-lived the particle is, right? So this is what to expect, right? And however, what happens, suppose the response is carried not by a single electron, but rather by like 2 electrons and a hole, right? Suppose if the responses can also be carried. So this is where this comes from, where this bump in the response comes from. If I look at imaginary, now if I look at real, of course it will go the opposite way. In the real, it will have the real GR omega K would look like this, right? If I plot it, it will look somewhat like this at omega K, omega star K. Again, it's simply the real part of this guy, right? 1 by x minus z will look like this. It will have a 0. The real part will have a 0 there, but it will change sign and have a structure like this, right? I'm just plotting the function. That's all. If I plot 1 over x minus z, where z is a complex number, so this will have a 0 at the real part, will have 0 at the real z, and okay. So that's obvious. So now what is happening here is that, okay, now if I impart a momentum k, now suppose I tell you that this system of particles, this 2 electron and a hole, they have total momentum k. Now, if it's a single particle, if I say that its momentum is k, then its energy has to be somewhat here. It can have a small width of possibilities, but its energy is more or less fixed up to that width, right? So, but if I have a 2 electron and a hole, and just say that I give a total momentum k, then the energy can be unbounded. Why? Because suppose I take like 2 particles and I say the total momentum is p. So now it means that the momentum here can be p plus k, and here the momentum can be minus k. And the energy here is p plus k squared by 2m, and here is k squared by 2m. So the energy can be whatever. Energy can be very large, right? So if I say this, but the energy of this system has to be greater than some threshold value, right? Typically, and the threshold value here is simply when k would be equal to 0. So the energy has to be greater than p squared by 2m, because one of the particle can have momentum. So there will be some threshold, and after that threshold, you will have a total energy can be anything, right? But this threshold can be plus or minus both, because suppose it's a hole, then it can be plus or minus. So typically what you will see is that for this case, the energy would start somewhere here. The energy possibility will be starting, and then all energies above this is possible. And similarly, there's a thing in the negative side, and then all energies like this is possible, right? So then, but now because all these particles are interacting with each other, just like the single particle, it will have a finite width, like they will have some lifetime. So all of this thing kind of shifts downwards, and then you get some. So this is like a branch point, and then you have from this branch point everything is possible, and this is going to carry the response. And this is the width of the finite lifetime of this multi-particle state, the specific multi-particle state. And so you'll see that it will have something like a branch point, and then everything is possible. But because branch cuts can be moved, as long as there is at infinity that is well behaved, if the UV behavior is well defined, so then you can actually put this branch cuts away and put the branch cut here. So this is the origin of this branch cuts, and these branch cuts are coming because of this multi-particle states. This is going to be very important for us later and this is true for any quantum filter, be it relativistic theory or non-relativistic theory, doesn't matter. This is a structure that you should expect. And these branch cuts are coming from the fact that you have a multi-particle state that are carrying the response, and these multi-particle states can have if I fix the momentum, it can have arbitrary amount of energy, but only above a certain threshold. And these are the 2 thresholds that bound the branch.
So could you repeat why there's unbounded energy?
As I gave this example, like you take 2 particles and I say the total momentum is p. So then it can be p plus k and minus k. One particle can have momentum p plus k, and the other has minus k. The total energy is p plus k squared by 2m plus k squared by 2m, which is unbounded, because k can be anything.
But that does not conserve any sort of energy.
It's not conserved. So that's the whole point. I mean, what do you mean okay? So these are short-lived particles that they're intermediate states. So by Heisenberg,
delta E, delta T for a short time. Okay, for a short time you can violate.
Yeah, because you're measuring the response after finite time. Any intermediate state is allowed. Okay. And but yeah, by the uncertainty principle. But obviously, the shorter the time scale it is, the more and more energy you can resolve, right? Because But otherwise, yeah. Yeah. So anyway, so that's obvious. If you do the Fourier transform, you will see that, right? Yeah. For example, when I do the Fourier, the oscillations come because of the sine omega naught comes from there, right? Anyway, so when you take, okay, the other way to see it is if you take long time, right? If you take long time scale, so in the retarded function, you see there is omega naught k by omega naught, right? If you go to very long times, what you can do, you can write this as t times sine omega naught t by omega naught t. And because this is large, it becomes a delta function in t roughly. So basically, it becomes proportional to time. Yeah, this response becomes proportional to time. And sorry, this becomes delta function in omega. Sorry, delta omega naught. Sorry if you want. That's what I want. So yeah, so this is how it goes. Okay, this is something related. Okay, so right. So let's now go to today's lecture. So let us do some quick recapitulation of what we have so far. So we started with the quantum harmonic oscillator, where h hat was Hamiltonian was h bar omega naught a dagger a plus half. And we could also have written it like this, half p square by m plus half m omega naught square x square. Yeah, but and then what we saw that if you look at the retarded propagator in real time, it looks like 1 by m omega naught theta t times sine omega naught t. And we also saw that the classical propagator, the classical retarded propagator is something like this. It is I'm sorry, I think I wrote something wrong. I think there's a minus h bar by m. The classical retarded propagator was simply this, theta t sine omega naught 2. And we've said that they're related like this, right? Because if I look at the retarded propagator in the quantum field theory, we defined it like this: trace rho beta, then minus I, and times theta t, where this is a density matrix. So there's an extra minus I firstly, and there is an extra minus compared to the classical propagator. I should have, where the classical propagator is simply the Poisson bracket of xt and x0, right? That should be the classical propagator. And so if I now convert, if I want to relate this to, I note that first in the quantum case, I have an extra minus sign. The definition is just for no good reason though. It's just for a matter of convenience in definitions. And then xt minus x0, this has an extra, when I convert the Poisson bracket to the classic, when I convert the classical, when I replace these two should be related by minus I h bar at the leading order in h bar. And there is no subleading corrections here, at least for the harmonic oscillator, it is exact in h bar. And then, so it should be simply equal to this times the G classical, right? GR classical. And therefore, there's an extra minus h bar that is sitting here that is not there in the classical propagator, okay? This is something we said last time also in the last class, but maybe I was not so clear. So one of the things that I did was in the beginning, when I defined the retarded propagator as a minus I by h bar below, but it is useful sometimes not to define with the minus I by h bar. So from now on, I would not put the minus I by h bar. Although in the real response function, you need the h bar actually, because I gave the general proof in the first few classes. Okay. All right. Now, let us come to the Feynman propagator. So the Feynman propagator was defined like this. It was equal to minus I, an expectation value for trace rho beta the time ordered product of x2 and x0. And we explicitly evaluated it. So first of all, we showed that both GR, GA, the advanced propagator, let us also define the advanced propagator for convenience. Advanced propagator would be simply trace rho beta I instead of minus I, and then xt, x0, the same object, but with a theta minus t. So this is related to the advanced response. If we can, which we can define by running back in time, just the same exercise that we did earlier. And then we have this G. So these are all XX. So GR, so this is the Feynman propagator. All of them satisfies the same equation, which is del t square plus omega naught square. G is proportional to, I think, okay, just writing proportional because there is, okay, I think that basically it should be h bar by m delta t. So all of them satisfy the same equation, which is this one. I think there's a minus I somewhere because I put a minus I. So I think you can fix the factors easily because we did this exercise. We did a derivation of this explicitly for the Feynman propagator, right? So all of them satisfy the same equation, but they are not the same simply because we're looking, it's a Green's functions for different problems. It's a Green's function for different things. So therefore they are not the same. So the time order propagator is about how the persistence of the vacuum or the persistence of the thermal state after a perturbation. There's amplitude for that. This is something we also proved. So this is something that, so we know what this means physically. And explicitly, when we evaluate it, right, when we evaluate the Feynman propagator explicitly, we find it is minus IH bar by 2m omega naught e to the power I omega naught mod of t e to the power h bar omega naught by t minus 1. This is something that we did it. We did it explicitly in the class. H bar omega naught by t. Okay. And the retarded propagator, of course, is easy. This was explicitly found out to be theta minus t, h bar by m omega naught, sine of omega naught t. So I asked you to, so if you can explicitly verify that this object also satisfies this, okay? You can explicitly verify that it satisfies the same equation, but we actually did, but in the class when we proved this, we use the Heisenberg equations of motion directly, not this formula. But you can also say that, see that this is the same thing. Okay, so I asked you to do the Fourier transform of this, and Priyanka has done it correctly. She sent me the notes. Did anybody else try to do the Fourier transform of this?
Yes, sir.
Okay, you did. Very good. So if you do it, I think the answer, I just worked it out. Let me see. Okay, let us start with the Fourier transform. So all of this. So in Fourier space, GR omega has the simplest form, which we already wrote. It is h bar by 2m omega naught and 1 by omega minus omega naught plus I epsilon and minus of 1 by omega plus omega naught plus I epsilon. And whereas for the retarded propagator, it is simply the complex conjugate of the advance is the complex conjugate, and it will turn out to be the split h bar by 2 omega naught 1 by. So this is something we also did in the last class by using the convolution theorem, and it's simply plus epsilon becomes minus epsilon. That's the only difference. Okay. But now let us do the Feynman propagator then. And the claim is, so I think this is also what was, so I did it in the morning today, and So I think this is what Priyanka got also. Let me see. It is this h power by m, and then we have 1 by omega square minus omega naught minus I epsilon square times 1 by 1 minus e to the power minus h bar omega naught by t, and minus of omega square minus omega naught plus I epsilon square, and e to the power h bar omega naught by t minus 1. I think this is what Priyanka also got. So I will explain how to get this. So to do this, all that need to do is to do the Fourier transform of this object, right? E to the power my I omega naught mod t, right? You have to do the Fourier transform of this and this. So let us do first e to the power I omega naught mod t. This is nothing but the e to the power I omega naught t theta t plus e to the power minus I omega naught t theta minus t, right? And now if I do the, let me see. Yeah, so now if I do the Fourier transform of this object, so firstly, yeah, I would simply get by the convolution theorem, this would be d omega prime by 2 pi, and then the Fourier transform of theta t. The Fourier transform, okay, the Fourier transform of theta t is 1 by minus I, 1 by omega plus I epsilon. And Fourier transform of theta minus t is 1 by I, 1 by omega minus epsilon, and delta t, sorry, e to the power I omega naught t would have the Fourier transform 2 pi delta omega plus omega naught, and like that. Okay, so now let us try to put everything together with this. So what is the Fourier, what is this? So first I can convolute with, so I get 1 by minus I times omega minus omega prime plus I epsilon. That first I take the theta and then I multiply the delta, then 2 pi delta omega prime plus omega naught. That would be the Fourier transform of the first term. And then the Fourier transform of the next term would be similarly plus 1 over I, and then omega minus omega prime minus I epsilon, and 2 pi delta omega prime minus omega naught, right? So that would be the Fourier transform of this object. And if I do this again, so if I do this, if I collect all the terms, I get, so, well, it's easy. So I would have to simply, I think this, so 1 by minus I is simply I, and I get 1 by omega plus omega naught, because first I should put in omega, I have to first simply put in omega prime is equal to minus omega naught here, right? I just simply put in omega prime is minus omega naught, and I get the first contribution, which is then omega plus omega naught. And these 2 pi's get cancels out. So I get simply omega plus omega naught plus I epsilon from this term. And the next term, again, I have to put omega prime is equal to omega naught here. And I get, but now I get a minus because it's 1 over I here, minus 1 by omega minus omega naught minus I epsilon. Okay. So that is what I get. So then this is nothing but I by minus I by 2 omega naught and 1 by omega square minus omega naught plus I epsilon whole square, right? That's all this is, if I write it together. So this is then, so you can substitute this Fourier transform of this e to the power. So first you have to take the Fourier transform of this, and this would give you this, what I just wrote, and then you have to do it similarly here. So and if you do it, you will get this, here you got omega naught. So, okay, the first term gave you omega naught plus epsilon square, and the other will give you this. Okay. So just do this exercise carefully. You should get this. Priyanka, do you agree with my computations now?
So there will be some terms in numerator also containing epsilon.
No, I don't think so. No, I think what I wrote here is correct. I checked it myself. So the point is that wait. So here you had a minus I. Sorry, here there was a minus I, and this will cancel with the minus I that comes, and there is a 2m. So there's a 2 omega naught. Sorry. Yeah, there's a 2 omega naught already here. Oh, sorry, what I wrote is incorrect. So this gives you, there is no 1 over 2 omega naught. Sorry, there is a 2 omega naught here. So no. And this will cancel with the 2 omega naught below. This will come cancel with this 2 omega naught here. So if you do it correctly, you will get, I think, I'm pretty sure, this object, what I wrote. Okay, h bar by m and this thing. There is no omega naught anymore because 2 omega naught gets cancelled. Okay, Priyanka? So good. So you will get this. I'm pretty sure about it. Just do it carefully. And don't ask me to check your algebra. Just do it. Okay, so this is fine. And so this is how you should get h bar by m. This thing is certainly you will get this. And I checked it in 2 different ways that this is correct, I think. Okay, so now you see what happens in the limit t goes to 0. So somebody was complaining that they couldn't understand the t goes to 0 limit. So first of all, you see that omega naught is always greater than 0 by definition. Here, it is an omega naught. So there's another way to write the same object using omega, but here I'm written only in terms of omega naught. So because omega naught is 0, it is easy to take the t goes to 0 limit. So when t goes to 0 limit, this term becomes 0, right? This term vanishes in the t goes to 0 limit, whereas this term becomes simply identity. Okay, so in the t goes to 0 limit, gxx omega would become h bar by m into 1 over omega square minus omega naught minus I epsilon whole square. Now the interesting thing happens when you have a relativistic particle. For relativistic, so the relativistic Hamiltonian is simply h would be some k h bar omega k, right? Omega naught k, and then a dagger k ak plus half. Or okay, I can forget the half if you like. I can keep it also. So now this omega naught k is what? Is simply equal to square root of k square plus m square. So I'm just using units where c and h bar is 1. If you want me to put back h bar, let me put it back. It's h bar square mod k square plus m square. And if I want to keep, I will keep c square here. There's an overall factor of c square, and I forget it. Yeah, there's a c to the power 4 and a c. I put c is equal to 1 to make my life easy. Okay, so this is what you get here. And now if I substitute it back, gxx, you see, okay, there is, I also put h bar to 1 for the moment. So we will do it carefully again when we come to the right stage. But it's nothing more than this. I mean, this is exactly the same computation. So I can do it rather quickly then. So you see that this becomes omega square, and this omega naught is omega naught minus I epsilon square is essentially will give you minus k square minus m square. And then there is omega naught minus I epsilon whole square, right? You have to take the, now if I take omega naught minus I epsilon whole square, that is nothing but equal to omega naught square minus 2I epsilon omega naught. But see, omega naught by definition is always positive. So if this is positive by definition, then this term that I get is nothing but plus 2I epsilon k square plus m square, right? But k square plus m square is positive, and all I need is small epsilon term. So I can write it like this, because a small quantity multiplied by some finite number is also a small quantity. So that what matters is simply 2I epsilon. And these things, you see, if I write it in what is omega square minus a square, if I use the signature plus minus minus, that's the more convenient signature to use. If you use the other signature, is obvious what will happen. If I use this signature plus minus minus, this becomes simply the 4 momentum square minus m square plus, again, the factor of 2 can be omitted because all that matters is a small number. So you get p square minus m square plus I epsilon in the t goes to 0 limit. And this is a famous Feynman propagator that you might have seen in many lectures or any, so this is a 1 over, this is a famous Feynman I epsilon prescription to find the time order correlation function. Okay, but the thing is that this is only true in the limit t goes to 0. Otherwise, you have the other stuff. You have the, if you are not at finite temperature, if you are at finite temperature, you actually find not only the I epsilon, but the opposite minus I epsilon with different weights. Okay. The other way to say it is as follows. As I said, so when you look into the poles and you look at GR, right, you have always the poles at omega is equal to plus minus omega naught. Like you can see here, when I look at the retarded correlation function, the pole is at omega naught and minus omega naught. Similarly, for the retarded propagator, omega naught minus omega naught, and same for this thing for the Feynman propagator also. So you see that when I look at omega naught minus I, so if I look at this object, omega square, so where are the poles of omega? Omega's right. The pole of omega here, okay, if I remove the intermediate stage computation, okay, so where are the poles here? So one of the pole is at omega minus omega naught plus I epsilon. If I write this down in a, the poles will be at omega is equal to omega naught minus I epsilon and at minus omega naught plus I epsilon. Okay, so for the retarded propagator, I move both the poles down for the retarded propagator at t is equal to, so this is for any t, any temperature. For the so this is at minus epsilon. So this is real omega, this is imaginary omega, and looking at the poles of GR omega. So they are all down in the lower half plane in order to get, because the GR omega has to be analytic in the upper half plane, simply because I argued earlier why it has to be. It cannot have any poles in the upper half plane because it vanishes at t for t greater than 0. So because of this causal property of GR omega, it cannot have any pole in the upper half plane. It should be continuous. I gave an argument because if you for t greater, yeah. So when for t greater than 0, for t less than 0, you have to close the contour in the upper half plane when you do the Fourier transform. And if it is analytic, it will not have any pole, and the answer will be 0 by Cauchy residue theorem. So if GR omega is analytic in the upper half plane, then only then it will give you a causal response. So this is then consistent with what we see. And then for the advanced propagator, both of these poles, which are omega naught and minus omega naught, here also, they are moved up, right? Whereas for the Feynman propagator at t, this is again at any temperature, but for Feynman propagator at t is equal to 0, what we're doing is that we're moving the positive energy pole down and the negative energy pole up. That's clear because only this term contributes at t is equal to 0, and these are the poles that you pick up from here, omega naught minus epsilon and minus omega naught plus epsilon. So I think you should understand this computation very carefully, okay? The computation that we have done here. I've taken some time to do it, but there's a very good reason I have taken a time, because this is a very simple quantum mechanics computation, right? You can easily follow it, but the exact quantum field theory computation is not complicated at all. It's exactly the same computation. And so if you understand this computation, you will understand the physics, okay, of what is happening. Okay, and why you have I don't know, I can't understand what you have written. Is epsilon less than 1? Epsilon is a very small positive number. Epsilon is greater than 0 and small. That's all that we require, right? I mean, this is something that we already, I think I defined epsilon already when I was long back in many lectures back. Anyway, so, okay, so this is the Feynman propagator. So up to here, any question about understanding these? Because these are going to stay with us forever, this Feynman propagator, and these propagators are very fundamental objects. Okay, I hope not. And I think this is a computation, just keep in your head and try to do it. Just not simply, my advice is that you try to repeat the computations on your own, because then it will sit in your head properly. Because once this computation becomes clear, then the derivation of propagators will also become clear in relativistic quantum field theory, or any quantum field theory for that matter. So this is a very fundamental thing. It's not like is different from relativistic and different for non-relativistic, except that when it comes to relativistic theories, you can write it in a more covariant language, more Lorentz covariant invariant language. That's all. That's the only difference. Okay. So before, okay, so then let us try to just recall one other thing, which is the G greater and G less, right? We saw that this is just simply just a quick reminder that this was minus I by h power 2 and omega naught e to the power I omega naught t by e to the power h bar omega naught by t minus 1 plus e to the power minus I omega naught t divided by e to the power, I think this is 1 minus e to the power minus h bar omega naught by t. And then similarly, G less xxt is equal to minus I h bar by 2 and omega naught. The same thing, but it is just t goes to minus t. So this is something we will show that's very general, that if you take t goes to minus t, this is okay. So that's what we see, right? And one of the things you can easily check that both G greater and G less satisfies this equation. G greater, G less T are both vanishing. Both should vanish, okay? But they are not the same objects, right? They're two different solutions to the same equation. And so there's a good reason why I'm writing it down explicitly, because we are going to refer back to it for some reasons in this rest of in the remaining lecture today. So then this minus I pi h bar by m omega naught delta omega plus omega naught by e to the power h bar omega naught by t minus 1 plus delta omega minus omega naught by 1 minus e to the power minus h bar omega naught by t. And t less etc omega would be minus I pi h bar by m omega naught. So I have worked these things out. I think there is no mistake in what I worked out. So all these things, whatever I'm writing today in the lecture should be all correct. Okay, so these are the things that we find for G greater and G less. This is going to be useful for us for what for something that we will see today later, and there'll be good reason I've written them explicitly. But this actually completes the list of all propagators that we need to do the Weeks theorem. So when you generally try to apply the Weeks theorem, that's all that you need: G greater, G less, and the Feynman propagator. Or there is some other basis where you read instead of G greater, G less, you can also use that retarded advance and Feynman propagator. So there are two ways to do the Weeks theorem, and these are the two different ways of writing it. Okay, so this is basically all that I have to say for the quantum harmonic oscillator. But today, what we are going to do before we go to the Weeks theorem, we try to understand more general properties of two-point functions in an arbitrary theory. So this is going to be very useful for us because why? Because suppose you want to use the Weeks theorem and try to compute, say, one of these objects. So okay, so I should have said something. I'm not. So you can ask, is there some independent physical meaning of this G greater, G less? So what we are going to see is that indeed there is, because G less is something that you can actually measure by for fermionic systems. You can measure by something called photoelectron spectroscopy. So essentially, the idea is very simple. You take a you take a you just take some sample of a material and bombard it by some photons and look at how many electrons are going to come out of the medium, which has this energy and this momentum. And this exactly is this propagator, is G-less propagator. So this, I will try to give a proof of this. Is actually rather simple proof, but I don't want to get into this right now. Maybe I should give you an assignment problem to work out where you see this as this thing. So each of these things is related to measurements, and so you can actually see so there are many interesting ways to understand the fundamental things of what the stuff is made of. What is it that is made of? Yeah, there's one more thing I wanted to tell you, that all of these things that I said, this idea of a branch cut is actually true only if you have quasi-particles. One of the strange things that you see is that when you take the other limit, strong interaction limit, when zk goes to 0, right? There is no quasi-particle pole. Then even the branch cuts do not even exist in this conventional sense. So instead of the branch cuts, you find something rather strange. You don't find this. You find something like a Christmas tree structure of more poles, which are, but these have, so the lowest one will have something of order of temperature and both a real and a negative part. So they look something like, they look like 2 pi nt 1 plus, sorry, plus minus, sorry, let me write it down. 2 pi nt plus minus 1 minus I. They look like this. Okay, these are the poles that you find typically. This is roughly speaking, this is how they look like. So this is how they look. So instead of branch cuts, you find a nice Christmas tree of pole structures at k is equal to 0, say, and at finite k they start moving because they have a dispersion relation also. So this is very weird, right? I mean, instead of branch cut, you find something like this. And they have a very beautiful interpretation, actually. So remember, I told you that in this limit, you could actually try to see the theory as a classical gravity theory in one higher dimensional space. And then these poles are nothing but the ringing modes, the quasi-normal ringing modes of the black hole. Because the black hole represents a finite temperature state in the theory, in the quantum theory. And these are exactly what so when people are measuring these gravitational waves, and when you have this, the last, so initially you see some kind of a waveform like a chirp. So there's the omega that is frequency that increasing with time. It's called a chirp signal. And then when the thing actually starts, when the thing, after they merge, the whole thing settles down to a proper black hole. And when it starts settling down to a proper black hole, you see these ringing modes of the black, which are these quasi-normal modes. And it's exactly this what you see. So it's beautiful, like so it looks like, so it's rather weird. Like you don't think that gravity can describe like a quantum field theory, which without any quasi-particles where Boltzmann equation fail, right? The very fact that they two have the same kind of analytic structure is rather surprising, but it's something that comes from the string theoretic duality, or this what I call this. But of course, in between, there of course, as I said, there's a modern research is to understand how can interpolate these two limits. How can a branch cut become a Christmas tree, right? This is something that we don't know yet, but this is one of the most fascinating subjects of research. So anyway, so this is something I just wanted to say before going to the more general properties, because I find this it's useful for you to know what is the modern questions people are also thinking about. But I think now you have some idea about how the general, what are the propagators and how they look like and all of this. Now, why we are studying general properties of two-point correlation functions? Because one of the things that we want to show, so there are many things we want to show. So one of the things we want to show, it is enough to just compute it is just enough to compute this. All the other propagators, so the Feynman propagator, the retarded propagator. Well, the retarded propagator is kind of obvious because you simply multiply this by minus I times theta t, right? But the Feynman propagator is not obvious, that how from this computation you can get Feynman propagator, right? And G greater xxt, all propagators can be obtained just from this. That's a remarkable statement, right? If you just compute this, that's all that you require, and that all that you need. And there's another interesting thing that we will see, that there's a very nice relationship between the commutator and the anti-commutator. And there's some nice thing which we will call fluctuation dissipation relation. And this is also something we'll see called this related thing called KMS periodicity or KMS condition. This is called Kubo-Martin-Schwinger condition. And these are very fundamental things because this leads to the fluctuation. This leads to all your high school physics. This is what we'll see, that it's a very fundamental thing. It's an extremely fundamental thing. So if you have seen the Einstein relation, if you take a Brownian particle, you see that the Einstein relation tells you that. So if you look at the particle, there is some it goes like square root dt, right? There's some diffusion constant, and the Brownian particle moves. If you start from here, after some time t, it will go like this, square root dt, right? And the Einstein relation tells you that x squared t is simply related to its diffusion constant by the temperature and all, if you remember. So I will state it. I have to remember exactly what is it, but it is times t, some d times t temperature will give you. So the similar thing is as follows, that if you take there's also a lot of similarities. So for example, take a thermal wire, you look at the fluctuation, the thermal fluctuation of the current, right? I square. So that is related to, there is, of course, the mean current is nothing but V by, that's Ohm's law. But then above the Ohm's law, there will be some thermal fluctuations. So Ohm's law is not exact. There will be some thermal fluctuations on top of it. And this is related to this conductivity, is related to the, or 1 over the resistance times the temperature, essentially. So all of this are basically classical laws, right? But these are simply quantum limits. If you take h bar goes to 0, you exactly get all of this relation. But when h bar is not 0, they give you a quantum generalization of this usual thing. So if the particle would have been a quantum Brownian particle instead of a classical Brownian particle, and but actually h bar is there in nature, right? It's simply that h bar is so small, so we don't need to take an artificial limit. H bar goes to 0. H bar is there. We cannot get rid of the h bar, even in a wire, right? So, but you will see exactly the quantum generalization of this classical relations that we have. Or the fluctuation dissipation relation. This is something. So actually, these two statements are related. The statement that everything can be obtained from the commutator is equivalent to these statements. Okay, and this is a very fundamental, extremely fundamental thing, and it is at the heart of understanding. Now, why this is important to understand also, because when you try to do if you want to do a computation of, say, I want to compute this object for interacting theory, right? I do a lot of Weeks diagrams. So what I'm going to tell you is sufficient just to compute this. If I compute the commutator, then I can obtain all the rest by doing suitable things, which I'm going to tell you now. So this is why the commutator is enough, right? This is a very fundamental statement. So it's enough to, and typically what we will see, the computing this commutator is simple. The simplest thing is simply to compute. And for that, you have a very nice formula. When we, at least at one loop, you can write down very easy formula. And so it's very easy to compute this, and we can simply compute this, and then the rest of the things we can obtain from that. Okay. So this is something useful to keep in mind, but this is true only for a finite when the state is in thermal equilibrium. If the state is not in thermal equilibrium, then of course you need to. But if the state is not in thermal equilibrium, away from thermal equilibrium, Well, then I think it is sort of obvious, because you basically need to do two things. You need to do the commutator and the anti-commutator. So by this, I mean it is xt x0 plus x0 xt. So this is something that you need to compute. You need to but this is sort of trivial, right? Because if I know if I know this, if I know the difference and the sum, then I can write anything as a combination. Or the G greater can be written as a sum, and the G less is simply a difference. So it's obvious. And then for t greater than 0, the Feynman propagate is G greater. For t less than 0, the Feynman propagate is G less. Right. So it's obvious that if I know these two, then I can know both. This is not a profound statement, right? The profound statement is that in thermal equilibrium, this anti-commutator and commutator are not independent of each other and related by what we call the fluctuation dissipation. Now, this object governs the causal response, and this object governs the statistical fluctuation. So what you show is that, but the imaginary part of the causal response in Fourier space gives you dissipation. How much, like, is related to the Joule heating by the wire because of our. So if time permits, I'll show you how this is related to dissipation. Not today, maybe. So the main thing is that when you the main and the crucial statement is as follows, that the statistical fluctuation is related to dissipation, right? And this is why it is called the fluctuation dissipation relation. And this is an exact statement in quantum field. This is something that we can prove. Now, when you go away from equilibrium, you have to solve these two things independently. So what I'm going to show you is that, and I hope to show you this course, this is not also included in a standard like Peschkin-Schroeder, but I think it's useful to know this. So actually, there is a way to do it. So there's a technology in quantum field theory. This is something that we will learn a little bit better. So one of the interesting technology is to construct something called the 1PI action, or the quantum effective action. Okay, so what's the point of it, right? So let me illustrate. This action would look something like this. S of x would be the standard Lagrangian that we see, dt half 1 over, sorry, half m x dot square plus v of x, sorry, minus v of x, right? Plus quantum corrections, which I call the quantum potential. But then there could be also higher derivative corrections, like x double dot square plus so on and so forth. So you will see some structure like that. So we will see how to compute it later along the course. So we will do it for scalar field theory explicitly. For scalar field theory, we will understand this explicitly. So the advantage of the quantum effective action is as follows. So the equation of motion for x, if I look at the average of x, can be computed okay, if I construct this, so that's a very interesting thing. So if I can construct the effective potential, then I can obtain this. Now for the harmonic oscillator, there is no correction. But if I put interaction, the quantum effective action is different from the classical action. Of course, because so we will know how to construct this thing, and we simply set this to 0. That is it. So I think Peschkin-Schroeder at some point will tell you this, of course. But okay, but then why I should not be happy with this? Why this is not enough? So the reason is not enough because if I actually do a measurement of x of t, right, it will not be the measurement. If I say I do a measurement, the measurement of xt will typically not be equal to x of t, right? It's simply the average value of the measurement. But it's not what I need to do. What I need to actually find is a probability distribution for the measurement of xt. So it would be always peaked at xt, but then it can be a very complicated distribution function like this, right? It will be, the peak would be at average, but then what I need to actually compute is a probability distribution. So in a way, what I need to compute is some of these, what I need to do is to compute like x squared t, x to the power 4t, and all of these, right? But this is not something I can get from the quantum effective action. To do this, what I need to do, I need to compute a correlation function and do it, and then take the equal time limit. So for that, what you can do is to do something more clever. It's called the 2pi effective action. In this 2pi effective action, what you can do, you can construct the action as a function of x, as a function of the commutator and the function of the anti-commutator. So let me define this as a commutator and call this as rho and call this as f. I can construct this 2pi quantum effective action like this, right? Now this is so then what I need to do is to solve all of this together. I need to solve this is equal to 0, this is equal to 0, and this equals to 0. I need to solve for all of this. Now, if I first solve this and I substitute it here, I should get nothing but the quantum, the 1pi effective action. So it will not contain any more information. So this 2pi effective action, if I just want to obtain x of t, it will have no more information than the already 1pi effective. But the new information that it contains is that it contains how the correlation functions evolve. For example, I would also be able to compute x squared t from here, right? By taking the coincident limit of f. So when if f of t is equal to xt x0 of, or I should rather call it ft t prime is equal to xt prime plus xt prime xt. Okay, so another thing that we have to keep in mind is that when we're away from equilibrium, we should put in both t and t prime because of time in equilibrium we have time transition symmetry. So therefore, this can only be a function of t minus t prime. But out of equilibrium, you need to keep both t and t prime explicitly. All right. So now the point is that if I take f to t prime and I take t prime is equal to t, I will get x squared t. So the only way I can do it is that I first take this. I have to compute all of this together. And see, I cannot just obtain f without computing rho. There is no way to do it. I have to solve for both rho and f together. And then when I do it correctly, I will get this. I'm able to take x squared t. But now you may not be happy. I need to also compute x cubed t, right? I need to compute x to the power 4t. So there is a very nice procedure like that to consider a generation called NPI effective action and do it. But so far and so people have not really, I mean, for all practical purposes, people only go up to 2pi. It's not like NPI is not interesting, but it's that people, I mean, anyway, these things are very harder to measure, right? And so and the interesting thing is to see is that so if you know how to compute it, and the other interesting thing is as follows. So normally when you do statistical mechanics in your statistical mechanics course, right? You always put the system as finite temperature, right? But you can also wonder what happens if I evolve the system, if I take a statistical ensemble and evolve the system. So if you do quantum field theory, you can simply take the limit h bar goes to 0 and obtain classical statistical field theory. And the only thing that will happen is as follows, because there will be no analog of the commutator that run in the loops, because you can simply take any quantum field theory, remove all and take a proper h bar goes to 0 limit in which all commutators drops from the loops, and then you get classical statistical field theory. So you don't have to do anything else. So basically, it's a very fundamental formalism that allows you even to understand fluctuating hydrodynamics. Because of this reason, that this is the same technology that you can do. So that's the beauty of it, of this subject. It's very fundamental subject, and it tells you how to kind of disentangle. This is the way of doing things, right? So the other way to do it would be that I look at x of t, and if I look at x of t, I will get an equation of motion for x of t will contain x squared t, x to the power 4t, right? And all of these are coupled together. So but what this technology allows to disentangle, because when I do at a one-point effective function, I can actually put all of these things in a construction called a quantum effective action. Now, this quantum effective action has a lot of beauty, right? Because if x is equal to 0, the actual system is not at exactly in the quantum potential where v of x is minimized, but where the quantum effective potential is minimized. It's not at the minimum of the classical potential; it's the minimum of the quantum potential. So even if you want to solve lambda x to the power 4 is equal to 0, right? This is your you will not be at the minimum of the actual classical potential. You will be at the minimum of the actual quantum potential, right? And actually, what that is also expected. Suppose you have a double well potential of this kind, you don't expect that the particle will be either here or here because of tunneling. It will be actually here in the quantum theory. So anyway, so this is something that is very interesting, and we should. So what we learn is that the quantum effective potential is different from the classical effective potential, and it's not true for the harmonic oscillator, but it's true for this one. So what we are going to do, we are going to learn all of this, right, slowly, and learn it in the context of field theory also, not only quantum mechanics, right? But you see, the basic technology is the same. But it's not like in field theory you have to do something more. So I showed you, for example, how you get the 1 over p square minus x, the Feynman propagator, right? You didn't have to do anything extra, right, to get the Feynman propagator. It's the same thing that we did, and so this is something worth keeping in mind. So although I'm doing quantum mechanics, actually we are doing quantum field theory. Okay. All right. With all these statements in mind, let us then start. So I hope you got some overview of how what kind of technology we want to learn, right? So it's not that we are only interested in compute S matrices. We're also interested to understand all of these things, like time evolution, how to follow. I take a many body system in optical trap. I want to understand how the system is evolving. I want to image the system. All of these are important, right, today. We cannot just simply, like, now even in particle physics is important, because people are doing heavy ion collisions. People are colliding stuff and creating new states of matter and trying to understand the time evolution. So we need to understand how things are not simply stupid S matrix, right? So we need to understand this. All of this. So we also should know how to do S matrix computation. They're also very important. So we are going to learn all of this stuff, right? And my idea is that instead of telling you how to do QED complete altogether, how to do fermionic things, I think what we should do is to understand the scalar field itself properly, and in the end to do this fermions. I'm not going to touch like QED in this course, because I won't have time for that. This will be relegated to the next course where we do path integrals and all of these. But see, I mean, this is already a lot, like you are learning a lot, right? Because these are the technology that's very fundamental. And once you understand it in a certain context, even if you understand the context of quantum mechanics, that's all you need. You don't need to, there's no separate conceptual things that happen as well. There is a separate conceptual thing to happen when it comes to renormalization. That is something that we will also understand. Okay. All right. So let's get started. So let us start with some very basic things, right? I take thermal equilibrium. So I compute an observable O of t in time, which is simply e to the power minus h by t. O. And here h is the full Hamiltonian, not simply the h naught. The naught, it can be, it doesn't conserve particle number, blah blah, O of t, right? So 1 over z. where z is equal to trace e to the power minus h by t. So the question that I want to ask is O of t time dependent? Can somebody answer the question? Does O of t depend on time? I claim it is not. Can you show it? It's not time dependent. So here O of t is any arbitrary observable. It need not commute with the Hamiltonian. So h comma O is not 0. It can be anything, but the average value is not changing. Can you prove it? Well, that's exactly what we expect in thermal equilibrium, right? If a system has equilibrated, the value of any measurement is not going to change. So you take any measurement, and one way to see the system is thermalizing is to see that that the average value of your measurement is not changing with time. But can you prove this? Who can prove this? You don't even need to touch your pen, this thing. This is simple. Write this as t trace e to the power minus h by t, and I write explicitly e to the power I h t by h bar o e to the power minus I h t by h bar, right? But then I use the cyclicity of trace, right? If I use the cyclicity of trace, I bring this here, and because all h commute with itself, it's simply to the power minus h by 2, and it's explicitly time independent. So even if this as a particle number doesn't commute with your Hamiltonian, it will fluctuate. It has classical fluctuations, but its average is not going to change. Okay. All right. So now let us try to prove something similar. So if I take a 2-point function of take a 2-point function O1 T1 O2 T2. So it is already ordered this way. So I'm taking a greater T greater. So this would be what by definition it is 1 over z trace e to the power minus h by t O1 T1 O2 T2, right? So using similar techniques, you can prove this is nothing a function of T1 minus T2. This would be exercise. So on Tuesday, I will give you an assignment problem with, so this will be one of the problems. I try to show this, it's rather trivial. It's a simple extension of this. You can easily do it, okay? So it will only be a function of T1 minus T2. So it's enough to just look at, this is something that we have used often. Okay. If you wish, I can write it like this, and then, all right. So now let us try to see something interesting. So let us try to define something called GAB greater. So GAB greater T is 1 over Z trace e to the power minus h by t, A of t and B of 0, right? So by time transition symmetry, all I need is it is T1 and T2 with T1 minus T2 is equal to T, right? This is the same as putting A at T1 and B at T2 minus T. Okay, that's all. Or T1 minus T, sorry. This is a T1 and T1 minus. Okay, so that's it. And so now let us then define G less AB should be equal to 1 over Z trace e to the power minus h by t. This is something we did also for xx, the definition. But here we do B of 0 and A of t. We just put it in the other way, right? So these are the definition, right? These are definitions. So now let us see something interesting, right? And this is the foundation of all of these properties. So all that I claimed earlier, that you can just obtain everything from the commutator and nothing else, is simply a consequence of this rather simple exercise. So now let us do something weird. Let us take G greater AB T minus I H bar by T and see what I get. So basically I'm analytically continuing to imaginary time, right? And with this specific thing. If I do this by definition, I should simply just follow my definition, 1 over Z trace e to the power minus h by t. And I should write a t minus I h bar by t b0. That's the definition of t greater. But now this would be nothing but, I have to simply do the, I take a of t and I do a time translation, right? So it will be e to the power h times h bar by h bar t. So h bar would get cancelled, a of t and e to the power. Okay, so there is a minus I and again a minus I, h times t, where and a t is nothing but h by h bar and t is h bar by t. And similarly here it will get plus, here it will get minus. So this would give you basically minus h bar h by t. And b0. But you see that so this and this cancelled out. So this is nothing but 1 over Z trace but this is nothing but, by definition, this is nothing but G less AB T, right? So one of the things that is, if I just simply take time and analytically continue it and add this extra piece, then I simply get G greater becomes G less, right? Actually, there's a diagrammatic proof of this. So what is happening when I do G greater, when I write G greater, in the Schwinger-Keldysh contour, if you remember, we used to put AT earlier and then B0 later, right? So now if I take T goes to T minus I H bar by T, what am I doing is that I'm taking this kind of, you remember there's an appendage, I take it somewhere down here, right? Because when I translate to T minus I H bar T, I sort of move it down in a way. And then this actually becomes earlier in the contour than this. So actually, this is a very nice way to see it, nice pictorial way to understand it. So when I read, so actually, what you see is that one of the interesting things that we'll see with this appendage, and if I look at the full propagator in the full Schwinger-Keldysh contour, Gx is, which I can call Gc Tt prime. This is periodic in T goes to, let me just put it as T goes to T minus IH bar by T. Because if I contour order, then G greater and G less gets interchanged. So you just hold on. So there's a more, this is a more elegant way to state the same thing. If you don't understand that, is fine. So essentially the KMS KMS condition is nothing but a statement of that. the 2-point function on the entire Schwinger-Keldysh contour is periodic. That is the same statement. But for the moment, we are stating it in this way: G greater T minus I H bar by T is G less T for any two operators AB. Okay. All right. But now what it implies in Fourier space, right? So in Fourier space, what does it imply? In Fourier space, this implies, okay, so again, let us go back to the definition of G greater AB omega. So if you remember we simply this dt minus infinity to infinity e to the power I omega t and G greater AB t. This should be the way we are going to do this. So now what happens if we shift, so suppose G greater ABT is analytic for imaginary t for in this strip 0 less than equal to imaginary t less than equal to h bar by t minus of, sorry, I should put it in this way. So I'm going to prove to you this is always the case by doing something called the Kalin, by doing the Kalin-Lehmann representation. I'm going to show that this is always the case. Suppose G greater is analytic in this strip. So basically it means that if I take real t and imaginary time, then it is analytic in this strip, which is here. So G greater t is analytic here, right? So for the moment, let us assume this is true. Okay, I'll show this indeed true in any quantum field theory, but just for the moment, I assume this is true. If I assume this is true, then I can simply now shift my contour, because so this is my contour of integration, right? When I do this Fourier transform using this contour, right? Then I can simply go like this down, and finish my contour like this if you wish. Or the other way to do it is as follows. This contour can be shifted downwards provided there's no contribution coming from infinity. Okay. I also assume that this thing decays in time. At very large time, this is going to decay. So I will not get any contribution from here. So if it is analytic in this strip, I can simply shift my contour downwards and do my contour integration here, right? So what I can do, I can simply shift my contour to minus infinity to infinity to t, and if I shift from t goes to s minus I h bar by t, I get the same integration as s, then e to the power minus is omega, right? And but I get an extra contribution, which is e to the power h bar omega by t, and then finally I would get g less. Okay, I will get g greater t minus I h bar by t, which is nothing but g less itself. Right. So then it becomes, I can take it out and it becomes e to the power h bar omega by t, and whatever remains is nothing but the Fourier transform of. So in real space, it becomes g greater ab omega. In Fourier space, it becomes this thing, g less ab omega. And this actually has a nice interpretation, because when you do this exercise that you can relate it to this photoelectron spectroscopy, you'll realize this is nothing but absorption and the emission amplitude. And in thermal equilibrium, they should be balanced by this Boltzmann weight factor. So this is simply the statement is simply that statement that it's simply a question of detail balance that you derive like this, right? But it all comes from, so now you see that it comes from the operator algebra. It's not something that, so you see the operator algebra is going to derive to you how the world actually works, right? So that's the beauty of it. So try to it's really stunning that you can get it like that. So this is a very nice relation. You see, G greater AB omega is e to the power h bar by omega. This is something also called the famous condition, but now written in Fourier space. So, but to get there, what I need to first show is that show that this statement is true. I didn't prove to you that this statement is true. So how can I prove this statement that it is analytic here? So for that, let us try to go back to the actual definition. So these are the things that you would like to also master, like to be able to give this general proofs of. So one of the interesting things is a lot of profound things that we are experiencing in real life is simply comes from analytic properties of correlation functions in quantum field theory. Yeah, so that's a very beautiful statement actually, and it's a very profound statement that that many of the, so we will see also when we come to the S matrix, enormous lot of properties that we experience in day-to-day life are actually consequences of analytic properties or analytic structure, right, of the correlation function. So let's try to see it here. For example, that this statement, so the KMS condition assumed that this is true, and we have to prove that this is indeed true. So let us show that statement. So for that, let's again write GABT in this way. This is by definition, this is 1 over Z trace rho beta for e to the power minus h pi t, and A of t, B of 0. Now, if I try to write it in this in real space, so what happens is it's 1 over Z and then sum n e to the power minus En by t, where En is at the eigenstates of the Hamiltonian, obviously, and then we have n at b0 n, right? Now I should simply insert a complete set of states here and write it in this way. It is 1 over Z sum n prime, and it should be obvious what am I doing, e to the power minus En by t, and plus I En minus En prime t by h bar, and then n a n prime b n. So what I've done here, I've simply written A of t as e to the power minus I h. I hope you're able to follow this, right? So are you able to follow this step to this step? Not. So to do this, I simply wrote, okay, if I want to give you the details, is as follows: A of t is equal to A e to the power minus I h t by h bar, e to the power I h t by h bar, right? I've inserted this complete set of states. So n A of t n prime would be equal to e to the power I En t by h bar, e to the power minus I En prime t by h bar times n A n prime, right? So I simply use that here and I got this. Okay. So now let us see when you expect this to converge, right? So now let us look at the exponent carefully. The exponent carefully is simply e to the power minus En by t, or maybe I should write it this way, minus En, and I have 1 over temperature and minus I t by h bar, right? And minus I En prime t. Okay? That's exactly this exponent. Now for the sum to converge, right? So if t is, if imaginary t is greater than 0, right? If imaginary t is greater than 0, then this is going to be, so this object is nothing but minus I n prime and t minus I, sorry, analytically continued t, this will be real t minus I imaginary t, okay? So this object is nothing but minus E n prime imaginary t minus I en prime real t, right? Have I done the right thing? Oh, sorry, it's a plus, real t plus I imaginary t. Okay. So this is en prime imaginary t and minus I en prime real t, right? So if imaginary t is greater than 0, so we also assume that all the energy levels are positive, right? So in quantum field theory, you can always do that. You can always normalize the ground state energy to 0 so that all the energy levels are positive. If all the energy levels are positive, then you see that you will create a positive exponent here if imaginary t is greater than 0, and this summation will not converge because it will because En prime is unbounded from above, from below. The lower thing is 0, but it can be arbitrarily large because the spectrum has no bound. And then this is going to be very large. This sum will not converge typically because these matrix elements are kind of things that don't grow with En very large. So these are expected to have some decay. So in terms of energy, these are not going to be unbounded. That's typically the case, right? And then, but then if this is En prime is unbounded, so therefore this summation is going to diverge if imaginary this diverges. Now let us look at here, right? So imaginary, this means that imaginary t is less than 0. But if imaginary t is 2 less than 0, then this also this also has to have now this also should have a. So now let us look at here, right? En multiplies 1 over t minus I by h bar real t plus I imaginary t. There's an overall minus sign here. That is this exponent that appears here. And here I get then minus En. Sorry, yeah. So I get here, so I get now minus En, and here 1 over t minus I plus I becomes again plus imaginary t by hr, and then minus I real t. So in this to converge, I need 1 over t plus imaginary t by h bar to be greater than 0, right? So which means that imaginary t has to be greater than minus of h bar by t. But we also already know that imaginary t has to be less than 0. So therefore, for the first exponent to converge, so it implies that the sum converges, sum over n prime converges only if you get the following thing: 0 is less than imaginary, is less than t less than 0. So this is so therefore this expression is convergent only there, right? This Callan-Lemon, this is a Callan-Lemon representation, and this Callan-Lemon representation then tells you that it is it is convergent there. It is convergent only in this thing, and then basically, okay. Then if you have to define it away from this limit, then you do analytic continuation. But this, but it can be analytic only in this strip, and because we proved that we have been able to prove that it's analytic here, we can also use this. So this manipulation that I did by pulling the contour downwards is justified. Okay. Okay, so that's basically it. Maybe today, because I already, I think I already said a lot of stuff, and the positive temperature. No, we are not considering negative temperature. That is for negative temperature is typically for crackpots. Let's then try to end here now. But maybe I can already tell you this fluctuation dissipation relation comes about because if you see the commutator rho of omega, it is nothing but G greater AB omega minus of G less AB omega times of minus I. Because, oh, sorry. I think I should have defined with this with a minus I. I didn't do it. Ah, shit. So when I define G greater and G less, because to be consistent with what I was doing before, I should have put a minus I here and a minus I here. Sorry for that, I should have done it. And then your commutator is nothing but I is GAB term minus GAB less. But not, okay. In that case, this Calendar-Eman representations are simply changes by adding a minus I, nothing else. No other change required. Okay, so then rho of omega is this G greater omega I times G greater minus G less. But we just showed that G greater is equal to, what did we show just some time ago? That G greater AB omega is e to the power h bar omega by T times G less, right? So this is nothing but I times e to the power h bar omega by T minus 1 G less AB omega by the KMS condition, right? Now, if I look into this anti-commutator f of omega, I can also do the same thing. So remember, the commutator is simply the commutator, and the commutator is simply this thing, the overall factor of half, and then there is again an I by 2, G greater AB omega plus G less AB omega by definition. This is anti-commutator, right? Between 8 here and so in that case, if this is anti-commutator, then again I can use this. This becomes I by 2, but e to the power a bar omega T plus 1 times G less AB omega. So now if I take f of omega by rho of omega, right, what I get? F of omega by rho of omega, this G AB less cancels out, right? And I get e to the power simply half e to the power h bar omega by T plus 1 divided by e to the power h bar omega by T minus 1, right? So if I now multiply both upstairs and downstairs, I mean, by e to the power minus h bar omega T by 2, h bar omega by 2T. So I would simply get is nothing but half cot h bar omega by 2T, right? This is exactly half of cot h bar omega. So then I get the fluctuation dissipation relation, which is the anti-commutator, has to be nothing but half of cot h bar omega by 2T times rho of omega. So this is the fluctuation dissipation relation. Now you see, how do I get the classical limit? The classical limit is simply I take h bar goes to 0, but cot h x in the when x is small is simply 1 over x, right? So this becomes what? This becomes, in this classical limit, h bar goes to 0 limit, this becomes 2T by h bar omega rho of omega. But you see that when rho omega by h bar is what has a classical limit. So rho omega by h bar omega in the limit omega goes to 0 is nothing but, this is something we are going to prove later, it becomes the dissipative coefficient. For example, it becomes a conductivity of the metal, 1 over the resistivity or things like that, or it becomes a D of the Brownian particle. So essentially, it goes to some kind of diffusion, something that governs diffusion and all this. So this is something we'll prove. Actually, in the next class, we'll prove this. So if you do this, then what happens is that if you plug it back here and I take this classical limit, so you see that this 2 will cancel out, and I get something which I call a general diffusion constant. So you will see that this fluctuation f of omega in the limit h bar goes to 0 will become nothing but D times the temperature, T times the fluctuation. Okay, this is a so this is the Einstein relation essentially. So f of omega is simply the jittering, the stochastic fluctuation that is related to the dissipation constant times the temperature. So this is how you recover all of known statistical physics just from this relation. But you see now it comes from operator algebras. It comes from the algebra of operators. So you see it's very beautiful that all of these are going to reproduce things that we know, right? Okay, so I will continue in next class and try to prove this and then start the proof of the Wick's theorem, which will take then two. So up to here, Madhav and Kabir are going to give us the notes, and the next classes will be done by somebody else. I don't know who. Let's see. Okay. All right. So that's all then for today, and we resume. Yeah.
We have a class tomorrow.
Do we have a class tomorrow? Okay, you want to have a class tomorrow?
No,
Then
sir.
we can continue.
I'm just asking.
Oh, yeah. We said that we should have. Okay, so I will put an announcement then. We can continue tomorrow. So then tomorrow we can go very slow and try to finish this part. And then on Tuesday and Friday, we will, Tuesday and Saturday next week, we are going to finish the Wick's theorem. Okay, that's probably a better way to do it, because I don't want to rush through these parts because these are very fundamental and important things. So one of the tasks you could do before the class on Tuesday is to just check that this diffusion dissipation relation is actually true. You can simply go back to the exercise, to these notes that I said earlier, and include it in your notes also, Lalwala and Madhav and Ravid. So if you look at these relations, you can easily see from like here, G greater, G less, that this general relation is true. If I take this translation, T by, you simply get this. If I take T minus IH bar by T, you get G less. Because if you multiply these expressions, e to the power H bar, e to the power H bar omega naught by T, you will see that these two things become interchangeable. It's a fun thing to see that all that you know will be recovered. And this general relation that I also showed you will also be recovered. If you multiply e to the power H bar omega by T, you will get here to here. So it is true for the harmonic oscillator also. It's a very general statement, which I proved. Okay. All right. So then see you tomorrow at 9:30 again, and we will complete the state, all these kind of. Okay. Bye. The recording.